Going into Chapter 3 now, Section 1, we're going to be looking at graphing equations, and we'll go through these objectives. We'll also take a look at this type of graph, which is a bar graph, where usually time, or ages in this case, along the horizontal axis here, and then amount in this vertical direction, and it's setting it into various age groups, percent of people who go to the movies. So if you wanted to say what is the largest age group of movie attenders, you'd probably pick 25 through 39. And then my group here, 60 and up. And another type of graph we run into is this one we see here, which is a line graph. Again, time is along the bottom, and then the amount along the vertical axis. And this is projected growth of Wi-Fi enabled cell phones in the US. And the trend is up, but you notice it seems to be leveling off. I think most people have them now. Okay, and they help us to present data and easily pick out trends and the most and the least and this type of thing. So we're going to go on to starting our lesson, in which we have Objective 1, plotting ordered pairs on a rectangular coordinate system. So what we'll do here is build a rectangular coordinate system, and we start this by making a horizontal number line, and then in the center of it we're going to put a 0 right there. So on this side, these are all positive integers, and on this side, negative. So we kind of lost where 0 was, right about there. And then to this horizontal number line, we're going to add a vertical number line. So we come up this way, and to keep it nice and straight, down this way, more or less. And this is a vertical number line, where up here we're going to have positive values, and then down here negative values. So we have successfully divided our plane into 4 regions by using 2 number lines. This is what a rectangular coordinate system is. Now, the horizontal axis is called the abscissa, the x-axis, and the y-axis, which is this one, is called the ordinate. And they intersect at a point right there, where the ordered pair for that point would be 0, 0. Now we've introduced this term ordered pair. The ordered pair is written in an order that x is first and y is second. Always the x is first, the y is second. This is an ordered pair. Now we also see that as we look at this quadrant, or at this rectangular coordinate system, it divides it into 4 regions or quadrants. And we label those quadrants using Roman numeral numbers. This is the first, this is the second, this is the third, and this one is the fourth. Now, what we're going to do in our next picture, or next page, is to actually plot some points that are ordered pairs on this rectangular coordinate plane. And let's do that. So there's a little summary of what we built in the previous page. And now we want to show you how to graph, let's say, the ordered pair -2, 5. Well, remember, this is x, y. We always do the x value first. So we start at the origin. We mentally go over 2 to -2, and now we go up to 5, and we just put a dot there. And you'll be doing this in MathLab as well. Now for another one in which we have 5, -2. Now 5 is our first member, so we start at the origin, go over 5, and then down 2, and then just click that spot, and that is letter B. So this is the protocol that describes how you plot ordered pairs. And the question might be, is order significant? And the answer is yes. It must be in this order to get the right points. If you switch them around, there's something else. All right, let's get. And again, you can always pause and read your textbook carefully, going over more information. And this is to say that it is significant, the order. All right, let's go on to example 1, where we're asked to first plot each ordered pair on a Cartesian, which is another name for the rectangular coordinate system, and name the quadrant or axis in which the point is located. All right, so here we see, let's just check it out here by letters. So 2, -1. So we go over 2, down 1, it's right there. 0, 5. 0, 5, right up there. Now they also ask which quadrant is it in, or which axis is it located on. So this, of course, is quadrant 4. And we get phone calls at my office here at home. And this is not in a quadrant. We say it's on the y-axis. And then -3, 5. So over -3 up 5 right there. This would be the second quadrant. Now -2, 0. So -2, 0. Now this one is on the x-axis. Now -1/2, -4. So we go over a little bit, halfway, and then down. And this is in the third quadrant. And 1.5, 1.5. So over 1.5, 1.5. And that's in the first quadrant. And you'll have practice in MathLab and when we do our mini lecture booklet. So here we're looking at, again, a line graph. This is real world data that in the year, which is our x value, 2013, we had our y value 57. So we go to 2013, we go up there, and then over here, that's where our 57 is. And this would reflect a typical line graph. Now a question might be, in which quadrant do you think this is? Well, if you said the first quadrant, you are correct, because both values are positive. Now, another type of data we deal with is in objective 2, determining whether an ordered pair is a solution for an equation. So what we have to do is take our values for x and y, and we have 3 examples here, substitute it into this equation. But I'd like you to take some notes on this first. And that is, as we look at this particular equation here, this is a form we're going to see it in quite often in this chapter. And the name of it is the standard form of the linear equation in 2 variables. And that is ax plus by equals c. So as you look at that, a is 3, there's the x. Here it's a negative instead of a positive, but that's okay. Now our y value is there, because there's 2 variables, x and y, and there's a 1 in front there. That would be our b value, and that would be a negative 1. And then our c, or constant, is a 12. So this is standard form in the short way of the linear equation in 2 variables, x and y. So with that as background, we're just going to, and I'll let the book illustrate this instead of my writing it out, because it's nicely presented here. Our x is a 0 from here, and our y is a negative 12. So if we put a 0 where the x is, this becomes 0. And if we put a negative 12 where the y is, now remember there's a negative in the formula, so here we have 2 negatives. So we use the rule of double negatives, give us a positive. 12 equals 12, and that is true. So that would be an ordered pair on the line of this equation. In the next one, we're going to put a 1 where the x is and a 9 where the y is. So we have 3 minus 9, which is a negative 6. Does that equal 12? No. So this is not true. And for this one, we put a 2 and a negative 6, substituting carefully. So 3 times 2 gives us a 6. Now the opposite of a negative gives us a positive 6. And does 12 equal 12? Yes, this one's true. So this will be one of the kinds of examples you'll get where you carefully substitute these values into the equation. And something to know about this equation, it's in standard form. Now our third objective is to graph linear equations. Now this linear equation is in standard form. That is ax plus by equals c. And a standard method of developing ordered pairs that we can use to get some points that we can then use to graph the equation is this method. And they go through it in some detail. I'm going to give you the shortened form. You make a little t-chart. Put an x there and a y there. Now a very good method when it's in standard form, as long as this value here is not a 0, is to put under the x a 0, under the y column a 0, and then just any other point. Let's put a 1 here. And now we're going to introduce these single substituted letter values into the equation one at a time and find the other letter. So let's do this first one. If x is 0, so here it's 0. If x is 0 right here, what would be my y value? Well, I have a negative y equals 12, but I want a positive y. So I'm going to divide what I have here, this little mini equation, by a negative 1, and it just reverses the signs. And I now have a positive y equals a negative 12. So I have 1 point. Now how about if y is 0? This is my second point. Now if y is 0, this becomes a 0 here. I'm just going to find what a positive x is by dividing both sides by 3. Here this becomes an x then. 12 divided by 3 is 4. So we have now 2 points. Actually, that's enough to graph in MATLAB, just having 2 points. We often ask for a third, so let's do this one. Now, we're going to use this equation. It would be 3 times 1 now, minus y equals 12. Well, I'm going to take my y over to this side to make it positive. I'm going to take my 12 over to this side and make it negative, just using some of the techniques we had earlier. And now this is 3. So when x is a 1, I end up with a negative 9. Is what y is. And they may have some of these here, right here. There's this one, and they have this one, and they have this one that we've done. Now you can do other points. So when you take these values and plot them on a graph where x is 0, y will be a negative 1. I'm sorry, a negative 12. When x is 4, right over here, y will be 0. Now let's pause there for just a moment. Can you see that at this spot, and this spot, this is where this graph, which is a line, which is an equation, will cross, in this case, the x-axis, and in this case, the y-axis. And these specific points are called, in this case, the x-intercept, where your graph crosses the x-axis, and this one here, the y-intercept, where the graph would cross the y-axis. And we have them right here. Now, the proper way of writing a y-intercept is we say x is 0, and whatever value you have for here is a b value. This symbolism indicates the y-intercept, 0, b. And you might say, how would we indicate the x-intercept here? Well, we use the letter A, 0. So whenever you see for x a 0 and a value for y, that's your y-intercept, the y-intercept. And you can take some notes on this. And whenever you see a value for x and then y is 0, this is your x-intercept. And we see this clearly on this graph. So once again, the technique for graphing, and it could be almost in any form, but this one is standard form, is you make a little T-chart. I would put a 0 there and a 0 there. This would give you your intercepts, and then any other point along the way. And you'll have practice of this as well. So as we continue to look at the text, we see they are introducing that this equation is called a linear equation in two variables. And they're introducing this concept of the linear equation in two variables in standard form. So this one's in standard form. This one's in standard form. Now we're going to use this in chapter 4 as well, and later in many sections in chapter 3. Now, these equations, of course, will relate to chapter 2 as well. And they're saying many real-life applications are modeled by linear equations. Suppose you have a part-time job at a store that sells office products. They would pay you $3,000, let's say, a month, and 20% of all your sales as your salary. And this could be represented as Y equals $3,000 a month plus 1/5 of X, which would be your sales. And you would then get, depending on the amount of sales, you would actually get a linear graph. And for instance, if you didn't sell anything, they would still pay you $3,000. If you sold this much, you would take 1/5 of that, which would be 200, added to this, and so on and so forth. This would make a straight line graph. And this would be your ordered pairs. So let's look at example 3, which is going to put this into its graphic form. And they want some work to support what is here. So let's pause to read it and then develop it. So here we would put 8,000 where the X is. I kind of rearranged this and you'll see why shortly. So 1/5 of 8,000 is 1,600. We add it to 3,000 and we get 4,600, which is what they're saying you would earn. Now, how about if you wanted to earn 5,000 per month? What would you do there? Well, in that case, you would subtract 3,000 from both sides here, because you want to earn 5,000. That would give you 2,000. And then we would just use the reciprocal here, or multiply both sides by 5. And we would get X, which is your salary, or not the salary, the amount of sales would be 10,000. So if you had $10,000 worth of sales in 1 month, then your salary would be 5,000. Okay, that is in the, and there is the 10,000. All right, let's go on to example 4, because now we're going to use that technique quite extensively of making a T-chart, putting in some values, and then getting at least 2, but we sometimes want to have 3. And our graph now is this one. And by the way, this is in a special form, so take some notes on this. And the official way to represent it is y equals mx plus b, and the name we give it is the SlopeIntercept Form. Now we had standard form, Now this is slope-intercept where we solve for the letter y. Y equals something. This is in slope-intercept form. So we're going to put some ordered pairs here. They're going to have a 0, a 2, and let's say a -1. Now they've done each of this, so we'll kind of speed up a little bit and saying here we get y is 3. Here y is a -1. And y is 5. So we only need 2 pairs in MATLAB, but 3 gives us a greater comfort that we are in a straight line. And when you plot it, it looks just like that. Now do you notice something right here where we have 0, 3? Well, this is in the form 0, b, which is our y-intercept. Now our x-intercept, we don't have it listed there, but it's crossing the line, and that's where it would be, but we don't have it listed here. And again, you'll be having lots to do like this, in which you make a t-chart, develop some points, and you might say, what values do I use here? Well, you can use any that are comfortable. You want them to be in toward the origin, not way out here beyond the extent of your graph. Now, one of the things I like to stress is when we are finding the x and y intercepts, which is what they're asking us to do now, we use this x and y intercept t-chart. So it would be a t-chart set up like this. We used part of this before. We're under the x column. This is going to be a 0. And this value for y eventually will be our b value. So this would be the y-intercept. And under the y column, a little further down, we put a 0. And later this will be our a value when we find what it is. And that's our x-intercept here. Now, there is a case where there is no b value out here. See, this would be where our b value is. If there is no b value, then we have to add one more point to this. So if we're dealing with a 1/3, to keep this out of the fractions, we sometimes put a 3 here. Oh, not there. Over here. So in filling in this t-chart then, and this is the equation they're giving us, they're saying y equals 1/3 x. Now there is no b value out here, so that's actually going to be a 0. And we'll use that later. Now, when this is a 0, then when we put x is a 0 here, 1/3 of 0 is 0, so our y value is 0. Now, if our y value out here is 0, and we take 1/3, flip it, take the reciprocal, multiply it by 3, 3 times 0 is still 0, so this one's 0. So basically what they're saying, when it's in this form, your line will cross the y and x-axis at the origin. So we need one other point. So if we put a 3 there for the x, here the 3's cancel out, this is still a 0 there, y will equal 1. So we now get one other point, when x is 3, 1, 2, 3, y is 1, right there. Now if we had another point, let's say 6, if we put a 6 there, this would be a 2. And that's the one they're plotting here. So remember, there's an infinite number of points along this line, You only need 2 in MATLAB to make a graph, and a third one helps to ensure accuracy. Okay. Now in your next course, they're going to do a lot of this kind of graphing, in which you're graphing non-linear. That is, the exponent on the x, instead of being a 1, is now higher than 1, 2, or even 3. So for these, you just need to have more points, which they're showing you here, putting in some values, getting some points, and pretty generally, if it's to the second power, they're going to be parabolas that look like this. The tip of it is referred to the vertex, and in this case happens to be the origin. That's the lowest point of the graph. Now, one kind of equation we didn't treat in Chapter 2 is when you have absolute value. So we see that here. The thing is, this absolute value could have been a positive or could have been a negative. So when you do your values, as they do here, coming out of this, your y value will always be positive. So you're going to get one line that looks like this, and then in a sense, since it's always going to be positive, normally it would be extended down here, but because it's absolute value, it always turns out positive, so it just brings them up on the other side like so. And for absolute values, equations, you always end up with a V-shaped graph like this. Now this is a little twist that they're saying negative. So for a graph like this, and I'll just sketch this one for you, your V-shape would be toward the bottom like this, opening toward the bottom. If this were positive, remember, we said it looks like this. But if there's a negative out in front, it reverses everything and brings your V-shape opening downwards. For those of you who have a graphing calculator, of course, there are windows that you can set up on it and do these graphs, plotting it in this form, which is SlopeIntercept. And in our textbook there are these exercises. So we'll go on now to our actual hands-on practice, a lot of it, with our mini lecture.